first example, and then example 3 is just more of something I want to discuss, but example 2 we'll go through. So as a review, because this is going to be continuing from what we already had answered in example 1, so we were given the function that represented the position of a particle. T is measured in seconds for time, S is in meters. So in case we need to use it again, we had found our velocity function and the velocity after 2 and 4 seconds. And then we had talked about how the particle is at rest when the velocity or the first derivative is 0, found at what times that occurred, and then talked about how the particle is moving forward when the velocity is positive. So we found that happens on the interval from 0 to 1, and then on the interval from 3 to infinity, or when the time ends. So then continuing with that in part E, and I realize this might be a bit annoying, it's on a different page, so if we need to use anything you might have to flip back and forth. But it says draw a diagram to represent the motion of the particle. So what I'm going to write down is we had found, well, some useful information. From the previous part in D, we found that the particle was moving forward when t was between 0 and 1, and then when t was greater than 3. And therefore we could conclude moving back or backward between the times 1 and 3. At time 1, time 3, that's where the particle is at rest, so it's changing the direction it's headed at those times. So how you're doing this, or one way to do it, and I'm not sure if you draw diagrams like this, since this is a physics application in physics, that I'm not sure. But I'm going to say here, this is going to be my starting point, so this is time 0, and I'm actually also going to write, so that you don't have to flip back and forth, what our position function is. I'll write that up here. So that was t cubed minus 6t squared plus 9t. So what I'm also going to include at this time is what the starting position is. So at time 0, if I were to substitute that in, I'm at a position of 0 as well. And then I know I'm starting out the position, or the particle. Again, what's happening is the particle is just moving back and forth in a straight line. So what we are trying to show is when is it moving forward, when is it moving backward, and then when is it moving forward again. So I'm going to show that the particle starts out by moving in the forward direction. And it doesn't matter how long you draw that out, but then I know when I get to the time value of 1, that was when the particle was at rest, and I can also show here that that's when it's changing position. So at 1, it's changing to now head backwards. So I'm just going to list what the position was at the time 1. So if I substituted 1 in for t, what would the position be? If I substitute in 1, it would be 4. So in that first second, it traveled a distance of 4 meters. Is what that's showing. And then I know it's going to start to move backwards, and now if I want to keep kind of my position drawing accurate here, I'm actually going to just find this off to the side. I know now from 1 to 3, it's going to be moving backward, but I just want to find what position it's at 3. So when t is 3, what is the position? Should be 0. Okay, so what that shows me if I'm drawing this diagram is now from time 1 to time 3, I'm just traveling back the distance I just traveled. So my time 3 would be here because it's at the same position as where I started. And then from 3 on, it's moving forward. So then I can end this diagram showing from 3 until whenever we cut off the time or whatever it might be, it's continuing to go forward.
What?
And this diagram can also help you in the next part with finding the total distance. So there are questions on making that diagram or thinking through the diagram. Yes. And so again, I know we're breaking this example up from Friday, but this we had found in the previous parts of the problem, so it's all kind of building too. And then in part F, it says find the total distance traveled by the particle during the first 5 seconds. And I did give a hint there that the total distance traveled during the first 5 seconds is not the particle's position at t equals 5. So this function that we're given represents the position or the displacement. It does not represent the distance that it has traveled. And hopefully you can even see that from the diagram we just drew, that when we substituted in the time value 3, if in fact this was a distance function, this would show that after 3 seconds it hadn't traveled anywhere. But that's not true. In those 3 seconds it had traveled forward 4 meters and backward 4 meters. So it had really traveled a distance of 8 meters. So for F, this diagram can certainly help. I'll also lay it out so you could find it without having to make a diagram as well. But to find the total distance, what we need to know, and this is using previous parts, again, you need to know where it's moving forward and where it's moving backward. So I'm going to break those into different time intervals. So I have the time interval between 0 and 1. I want to find the distance traveled in that first second, because I know here it's moving forward. And then I want to find the distance traveled in the interval next where it's moving backward from 1 to 3. I'm just going to put back here. And then the distance traveled, and it says the first 5 seconds. So my next interval would be from 3 seconds to 5 seconds. Because I know here it's moving forward again. So I'm not just plugging 5 into my function and saying this is the answer. I'm finding the distance traveled over these 3 time intervals, forward, backward, forward again, and then adding those 3 distances together. So the distance traveled in the first second, I know we have it from up here, but how this would be laid out mathematically would be the absolute value of the difference between these function values, so the absolute value of f of 1 minus f of 0. So its position at 1 minus its position at 0, and then absolute value because since the function is displacement, that could come out to be negative, but distance should be positive. Negative would just mean it's moving backwards. So f of 1, that was we had that from above, that was 4. And then at 0, that was 0. So that total distance in the first second was 4 meters. And then from 1 to 3, so again, we can look at the diagram, but say you didn't make that or didn't have it, this would be another way to calculate it. You would take the absolute value of the position at 3 seconds minus the position at 1 second. At 3 seconds, we know that its position is 0 again because it's gone back to where it started, minus the position at 1 was 4. So this would be the absolute value of negative 4. That just shows it moved back 4 meters, but it still went a distance of positive 4 meters. And then from 3 to 5 seconds, we need the function value at 5 seconds. the position at 5. Should be 20. So the 5 is just substituted into our position function again. So at 5 seconds, it would be at 20 meters, minus at 3 seconds, it was at 0. So in those last 2 seconds, it traveled a distance of 20 meters. So then overall, if we total this, in those first 5 seconds, it has traveled 28 meters. That would be the total distance traveled. Yes, Connor. Well, this is showing, because if we did that, so what's happening is it is starting at 0. It's going forward, and then backward, and then forward again. So if you did just draw it in a straight line, you'd just be drawing a straight line. So we actually want to show where is it moving forward, where is it moving back, so you can actually see it, but knowing that it would be along a straight line. This is just showing, this would not be the graph on the x or y axis. The graph on the x or y axis would be the graph of this function. But this is just showing, so from 0 to 1 second, it's moving forward. And then from 1 to 3 seconds, it's moving back to where it started. So along our straight line, say this is the position 0 and this is 4. So in the first second, it made it to here, and now in the next 2 seconds, it's making its way back to its starting position, and then from 3 on, it's going to continue going forward. So this is just showing exactly where it's going forward and backward. This would be like if you were graphing on a coordinate plane, this would be the graph of your position using that function. So it's a diagram of where it's moving forward and backward, but you don't just want to make a straight line because that's not really showing you where it's going forward and backward. Does that make sense? Okay. And this you could also use to help you here. Because we made this, we can see in that first second the distance is 4 meters. From 1 to 3, going backward, it's going 4 meters. And then we just had to find from 3 to 5 how far it's going. So it's kind of tying into finding the distance too. This really shows that after 3 seconds, the distance was 8, even though the position at 3 is 0. But it still went 8 meters. Does that help? Okay. All right, and then for part G, how do you find acceleration? It says find acceleration at time t and after 4 seconds. So how do you find acceleration? So this would be, I'm just going to write down, we had found the first derivative, which was velocity. I'm just going to write down what that was because, again, I know that's on the front side. So that the velocity was 3t squared minus 12t plus 9. So that was really f prime. And so acceleration would be the second derivative, which would be what? What would our second derivative be? 6t minus 12. So this would be the acceleration at time t. So that's just asking for the function. And then it asks specifically after 4 seconds, we could just substitute in 6 times 4 minus 12. So 24 minus 12 is 12. And what would the units on the acceleration be? Meters per second, or meters per second squared. And then the last part, this is something we haven't talked about in here yet. When is the particle speeding up and when is it slowing down? Does anybody know how to determine where it's speeding up? We'll start there. Kind of. It's not only focused on the second derivative. I didn't know if anybody knew. That's why I was asking first. So, a particle is speeding up when your velocity and acceleration have the same sign. So if both velocity and acceleration are positive, it's speeding up. If both velocity and acceleration are negative, it is also speeding up. It is slowing down when velocity and acceleration are opposite signs. Okay, and this does come up. It's not just an application we talk about here and then you never really see it again. It doesn't come up a lot, but it does come up. I have seen it on AP questions, knowing when it's speeding up or slowing down. So knowing speeding up is not just when acceleration is positive, it's when both velocity and acceleration have the same sign. So both positive or both negative. So we already know we're going to find where it's speeding up, and then you can just use the opposite intervals to see where it's slowing down. We already know where the velocity is positive and negative. So we know that velocity is positive. We found that in part D for the intervals when t is between 0 and 1 or greater than 3. So that we had already found. So then we could conclude that velocity is negative when t is between 1 and 3. So we just then need to find where's the acceleration positive and where is it negative. And then where is that overlap. So if we have our acceleration here, acceleration is 6t minus 12. So acceleration will be positive when 6t minus 12 is positive. And if we solve that for t, that would be when 6t is greater than 12, so when t is greater than 2. So that's when the acceleration is positive. So knowing that, we have to find the intersection of these intervals to know when both are positive. So I'm going to make a note here. I'll put speeding up. So what is the overlap of these intervals where both velocity and acceleration are positive? When t is greater than 3, they're both positive. So we know it's going to be speeding up when t is greater than 3. Do what? This? Okay. I've just done it enough. I don't know. And then, so then acceleration will be negative when t is less than 2. And we could conclude being less than 2 really means you're between 0 and 2. So where is the overlap here? Between 1 and 2. So where is the particle speeding up? When t is between 1 and 2 or greater than 3. And therefore it would be slowing down. Yeah, so it is both of these because t greater than 3 is where they're both positive, 1 to 2 is where they're both negative, so it's speeding up on both intervals. Slowing down then would be between 0 and 1, so just filling in the rest of the intervals. So between 0 and 1, it must be slowing down, and then also between 2 and 3, it must be slowing down. So anywhere it would not be speeding up. Oh, all of those parts. Yes. Now, would that all be one question on a test? No, but all right. Are there questions on any part of that? Some I know we've already talked about. Some ideas behind how to solve these might be new. Yes, Dylan. T is a time though, so a negative time wouldn't make sense. It's what? Oh, yeah. Yes. Yep, so we're not using negative T values. All right, and then example 2. This is a much quicker example. But again, this is applying anytime you are asked about a rate of change. As long as the rate of change is instantaneous, it's the derivative. So example 2 says a company makes computer chips from square wafers of silicone. It wants to keep the side length of a wafer very close to 15 millimeters. And it wants to know how the area, A of x, of a wafer changes when the side length x changes. So it says find A prime of 15 and explain its meaning in this situation. In order to find A prime of 15, you need to know what A prime of x is. Okay, so we want to first, they're not giving us a formula for A of x, but we can find it. A of x is the area of a square. And since they are calling it A of x, it must be with a side length x. So what would the function A of x be? X squared, area of a square. Okay, so that's our A of x. So to find A prime of 15, you find A prime of x first and then plug 15 in. You don't plug 15 in first because then you're just going to have a constant. And the derivative is not 0. So what would A prime of x be? 2x. So then A prime of 15 is 2 times 15, so it's 30. What would, because then it says to interpret or explain the meaning, what are the units on A prime of 15? It's a rate of change, so it's a unit per a different unit. It's millimeters squared per millimeter. So you would not write it as just millimeters. I mean, yes, it would simplify to that, but you'd want to show that it is a rate. So it's the change in area over the change in the side length. And then explaining the meaning in the situation. We've had questions like this before. When you explain the meaning, you want to include, if it's A prime of 15, you have to include how the 15 ties in to then the 30 millimeters squared per millimeter. And if it's a derivative, it's not, or it's showing either an increase or a decrease in something. So since it's positive, it's showing an increase. So we could say to tie in the 15, the 15 is representing the side length of the square. So I can say when the side length is 15 millimeters, the 30 millimeters squared per millimeter is showing the increase of the area per increase of the side. So when the side length is 15 millimeters, the area is increasing by 30 millimeters squared per millimeter. So at that at that side length, that is showing the increase in the area, or the rate that it's increasing by. Questions on that? All right, the last question, B. It says, show that the rate of change of the area of a square with respect to its side length. That is the derivative. The rate of change is a prime of x. Show that this is half of its perimeter. So if this is our square, what's the perimeter? 4x. If you take half of your perimeter, that's half of 4x, which is 2x, which is a prime of x. And done. So that's all that's asking. To show that it's half the perimeter, you're showing that half of the perimeter and the rate of change of the area that you just found, they're both equal to the same thing. They're both equal to 2x. All right, and then example 3 isn't an example that I need to go through with you, but there is a problem on the worksheet that talks about current. So I just wanted to discuss current and how it is a rate of change. So it says a current exists whenever electric charges move. And then it says if the delta Q, so if the change in Q is the net charge that passes through a plane surface during a time period change in T, the average current during this time interval is defined as, so average current is change in the charge over the change in time. So therefore, making this into a limit, or taking the limiting value of your average currents, the current then is the rate at which charge flows through a surface. It tells you what it's measured in. It's measured in units of, this should be, I thought I changed that, charge, not change. Units of charge per unit of time, so it's often coulombs per second, called amperes. However, what's important for you to know, current is usually represented with I, but current is the derivative of charge. So if you are given a charge function, so if Q of T represents an electric charge and you are asked to find the current, you are asked questions then about the derivative. The current is the derivative of charge. So it's not as, I guess, as popular an example. Like physics, we use position, velocity, acceleration often. So I wanted you to understand the relationship between charge and current, and there is a current question on the assignment. So you can understand that it is the derivative.